It's my great pleasure to introduce the next speaker, Jovana Milić. And actually, it's your first time at AMOLF. Really happy that you're here. But your devices have been here for a long time already. So we're collaborating for many years now, and they've been tested over there in the lab. And I'm so very happy that you finally also made it in person, not just in device form or in online form. So Jovana is leading the Smart Energy Materials Group at the Adolphe Merkle Institute in Fribourg. Switzerland, beautiful place, if you have a chance. It's a very nice institute, a bit like AMOLF in terms of size and focus. Yeah, she's very successful and really one of the up-and-coming future leaders. Also has been awarded the Future Leader Prize from the ACS Society and many other prizes. I will not read them out. Maybe just a few. Helvetica Prize, Green Talent Award. She's part of the Swiss Young Academy, the Global Young Academy. So really. Clearly one of the up-and-coming future leaders in the field. And if you look at the field, it's perovskites, so we've already seen the importance of perovskites, but in a fairly broad sense, so working a lot of supermolecular chemistry, working on 3D perovskites, 2D perovskites, solar cells, other devices. So I'm really curious to see what you have to say today, and I don't really know what you have to say, but I'm just very curious. So the floor is all yours.
Bruno, for this kind introduction, and thank you for the invitation. It is a real pleasure to be here after so many years of indeed collaborating and interacting, and also to meet you all on the occasion. Now, it is further my pleasure to now complement this more global, zoomed-out perspective of the importance of this research and relevance of it all the way down and zoom in to the molecular level and provide you with more insights on the capacities of perhaps enhancing the functionalities of some of these materials while having these global perspectives in mind, but also going beyond the renewable energy conversion in photovoltaics and stimulating perhaps some of the creative thinking and innovative perspectives of these materials and technologies. Now, before I proceed, I would like to acknowledge that this work has primarily been performed in Switzerland at the so-called Adolphe Merkle Institute, Bruno already mentioned, in Fribourg, so central Switzerland, central west, at the University of Fribourg, where I'm privileged to lead the Smart Energy Materials team that is generously supported by the Swiss National Science Foundation, but a number of both national and international partners, particularly revolving around these bio-inspired materials centers, with aiming to learn from nature, but also a number of international and national collaborators, including those at EPFL, with whom I remain affiliated as co-supervising a number of students in the also extending this team of the Adolphe Merkle Institute, some of whom are highlighted here, including those at the Laboratory of Photonics and Interfaces of Professor Michael Gretzel, in the group of Lyndon Emsley with generous support on the NMR spectroscopy that I will be talking about a bit today. Also Ursula Röschelsberger with the theoretical support, and Jacques Moser for the ultrafast spectroscopy, including a number of international partners, some of which I highlight here as they are related directly to the work that I'm going to detail today, including those at the Max Planck Institute for Solid State Research, PSI and Nicola Cassati's group in Switzerland, and also, of course, some of the people you might recognize here today, being Bruno Ehrler's group and particularly Rita Muscarella, who is no longer here, but had a chance to interact with in the course of the past years at AMOLF. So this is also to highlight another perspective apart from the importance of the materials and the fundamental research, being the internationality and collaborative approaches that are relevant for addressing some of these complex challenges. Now, we are gathered around a shared vision and maybe overreaching objective to control complex molecular assemblies in order to address a specific function now at the molecular, but also material and ultimately operational device level, with the purpose of now developing also smarter materials that can respond to different external stimuli and also adapt to their operating conditions, while maintaining these functions even in functional devices, including those of solar cells or in photovoltaics. Now, the inspiration for this research often comes from nature. Even though these systems are not as effective as artificial technologies, they're remarkably adaptive to a variety of different external inputs and environmental conditions, which often involves the role of specific strategies related to so-called supramolecular chemistry, or non-covalent interactions that are at the core of controlling a number of complex biological processes, including those of, well, natural photosynthesis, which has in fact inspired the development of a number of artificial technologies for energy conversion, including those in photovoltaics. However, unlike the photovoltaic technologies where solar to electric energy conversion is exploited, these now photoinduced electron transfer cascades are in natural systems used to produce, well, chemical energy, which involves the role of very unique components known as molecular machines, such as the here illustrated famous ATP synthase that stands alongside other powerful biological machineries that comprise of these complex, non-covalent assemblies of functional molecular components that are at the core of the energy conversion process, and which now stimulate the development of other artificial molecular machineries that operate under comparable principles of tuning these non-covalent interactions between complementary molecular components in order to address a specific function at the molecular level, which is really at the core of our research pursuits, that evolves around this question of whether we could truly repurpose these bio-inspired supramolecular tools in order to address some of the challenges associated with artificial technology for energy conversion, while opening the path to perhaps smarter, more adaptive nanotechnologies. And similarly to natural systems, which do not involve either organic or inorganic materials, but rather hybrid, organic, and inorganic systems, we're also focused on hybrid organic-inorganic materials, and in particular, framework materials that enable realizing some of these dynamic functionalities in response to external stimuli, even in the solid state, that is especially relevant for functional devices, including those in energy conversion. And for this purpose, one can consider a range of different framework materials that are typically defined by these well-assembled lattices comprised of specific nodes and tailored linkers, and which enable tailoring this dynamics across different length scales and well beyond this classical random vibrations and towards more restricted, controlled, and even directional dynamics and motion in these systems to realize some of these functions that can be enabled across different framework material classes. What we commonly think of in the context of framework materials are metal organic frameworks or covalent organic frameworks, but also zeolites as well as hybrid perovskites that we have already heard about fill this class of framework, dynamic framework materials that can fulfill some of these functionalities, and which I would focus on today. Now, these are particularly relevant in the context of their importance in renewable energy conversion, or perovskite solar cells that we have already heard a bit about, which have emerged a bit more than a decade ago, but already over the past few years managed to challenge the performances of some of the commercial technologies while rapidly approaching these theoretical limits, while offering at the same time a much more cost-effective and the solution processable thin film technology that has stimulated unprecedented interest in the research community. Now, this is especially related to the unique characteristics of these photoactive absorber layers, namely metal halide perovskites, some of which we have already heard about, including this remarkable absorption, long-range charge carrier lifetimes, and also exceptional defect tolerance that has already been emphasized, that has really stimulated this interest across different research disciplines in the context of these materials. Now, they're here illustrated by their crystal structure that is commonly defined, now diving deeper into the material characteristics, by this cubic crystal structure defined by the AMX3 formula, typically referring to this corner sharing octahedral framework that is defined by this metal halide containing the species primarily lead and tin and different halide anions, while hosting in this central cuboctahedral cavity A cations that can be either inorganic species like cesium or small organic molecules as metylammonium or formamidinium, which really render these systems hybrid organic-inorganic materials. Now, what is especially fascinating about these materials that goes beyond their utility in photovoltaics is that now these hybrid, crystalline, and ionic materials are at the same time soft and dynamic materials that feature also mixed ionic and electronic conductivities, as well as the capacity to adapt to a variety of dimensionalities that really provides this rich platform for function-driven material design. Now, while some of these attributes have also contributed to the utility of these systems and their multifunctionality in the context of their application, not only in photovoltaics, but also light-emitting diodes, sensor, photodetectors, and more, they're also associated with, well, one of their major challenges that we are all painfully aware of, which is in fact their limited stability, leading to now their performances across these different functionalities and device architectures to gradually decrease over time, especially when they're exposed to external environmental factors in the form of oxygen or moisture due to the reactivity to these factors, but also as a result of these internal ion migrations within the hybrid perovskite layer that is now here schematically represented inside these typical photovoltaic devices when they're sandwiched between different selective charge extraction layers, but also across these layers that is actually accelerated under the operating conditions of now temperature changes, voltage bias, or light, leading to a number of degradation processes that poses one of the main challenges in this research domain. And in the face of that challenge, in fact, that has been attempted to be addressed in the community by a variety of different strategies. Some of you might be familiar with from compositional engineering, so using now these mixtures of different cations or anions to reach the most stable architectures, studying different device architectures or interfacial engineering to tackle this. This has been so far primarily driven by this strive to reach optimal device performances, while many of the underlying mechanisms are still not entirely well understood. Furthermore, many of these attempts to really stabilize the resulting structures or devices often come at the expense of the resulting performances that really still poses an ongoing challenge. And facing this challenge over the past few years, we have relied on a unique toolbox in an attempt to address it that I'm hoping to discuss a bit more today, which involves, well, supramolecular chemistry, which is here now very schematically illustrated by this, well, Swiss knife of different non-covalent interactions. Some of you might recognize, such as hydrogen bonding, halogen bonding, pi-based interactions, or others, whose now versatility and adaptiveness enables the development of a number of different functional materials, but also smarter nanotechnologies. And which now becomes increasingly relevant in the context of hybrid perovskites, and it enables now tailoring these interactions between different complementary components in both solid state, as well as between the corresponding building blocks in the solution processing of these systems, such as designing small molecular modulators that can, for instance, interact through some of these tailored interactions with the surface of hybrid perovskites, templating their structure, and now affecting their functionality at the molecular level that can be translated into a functional device operation. Now, in terms of these functionalities, as I realize that this is also a rather broad audience in terms of different research directions that are taken when it comes to tackling some of these technologies, over the past years, we could identify three key groups of functionalities that can be controlled through these approaches that I will just briefly outline, including the morphology control of these materials, defect passivation, so suppressing some of the defects responsible for the losses in performances, and overall stability enhancements either against the external environmental factors or the internal ion migrations. Now, each of these general group of functionalities can be now translated into a set of complementary supramolecular tools to address them, such as, for instance, using hydrogen bonding to tailor the morphology of these systems that directly relates to the role of these interactions in crystal engineering, such as directing these structures, but also indirectly affecting their optoelectronic characteristics, which are in fact primarily these materials defined by these metal halide orbital overlaps, and consequently being affected by the corresponding octahedral connectivities in these systems that can be controlled through some of these non-covalent interactions. Furthermore, relying on other, maybe unconventional in this context, non-covalent interactions such as halogen bonding or pi interactions to suppress some of these defects, or finally, relying on the assemblies such as van der Waals assemblies, more hydrophobic systems to increase their resilience against moisture, or control some of these ionic migrations, such as through strategies including host gas complexation that we have been particularly invested in lately. Now, ideally, a molecular modulator is supposed to simultaneously meet all these challenges and functionalities. And with the purpose of developing some of these systems over the past years, we have looked into a number of different small molecular modulators, from those relying on hydrogen bonding, pi-based interaction, van der Waals assemblies, halogen bonding, and others, each of which now demonstrating a variety of perspectives and opportunities to really control these systems, as well as their resulting stabilities, which it highlights the importance of two particular considerations when it comes to controlling or achieving supramolecular control in these systems, involving the role of different non-covalent interactions and their templating effects in terms of directing these structural components, which is something that I will primarily address today by providing an illustration of these factors through two groups of examples. Firstly, illustrating in principle how, in practice, these molecular modulation components or approaches work, and ultimately how they set the stage for enhancing the functionalities of these systems that go beyond addressing some of these existing challenges. Now, when it comes to molecular modulation, I will focus on the recent example of host-gas complexation, and similarly to the other examples in the spirit of this conference and the community, or the aim of bringing the community together, all the examples that I will illustrate, in fact, one way or another relate to the collaboration with AMOLF in order to really highlight them and also stimulate further interactions in the future. And one of them is indeed the role of these host-gas complexation. Now, being aware that not everyone is perhaps familiar with these concepts, host-gas chemistry has a very long tradition in supramolecular chemistry, and most of you might be familiar with, which refers to the formation of such host-gas complexes between a often pre-organized and typically macrocyclic host and a geometrically compatible gas moiety through now different non-covalent interactions. Now, with this broad definition in mind, we might view even hybrid perovskites as host-gas complexes of such an inorganic framework hosting central A cations. So truly ubiquitous in nature and material science, responsible for a number of biological functionalities, as well as in material science and artificial molecular machineries, for example, which I've been particularly invested in. So I use here as an example of one of such molecular machineries, which has been designed mimicking some of the interactions inside the photosynthetic reaction center that are now translated into design of this molecular system and a tailored interaction, enabling it to controllably expand and contract in response to different external stimuli, in particular electric charge or light, and as a result encapsulating these smaller molecules that can then be released on demand, which is of interest to a number of perspectives from molecular sensing, recepting, nanoreactors, or perhaps elements in nanorobotics. Now, learning and inspired by these systems, we've been asking ourselves, can we achieve some of these dynamic controls inside the hybrid perovskite framework by controllably binding and delivering specific ions inside the hybrid perovskite material, even in a functional device during operation? And to illustrate this, we focused first, considering especially the complexity and the steric demand of these systems, we have looked into a number of macrocyclic potential hosts based on their geometric compatibility, primarily involving these relatively simple now crown ethers that you see here, selected on the basis of complementarity with two specific defects on the surface of hybrid perovskites, which is uncoordinated A cations and lead cations, which now, applying this system at the interface between the hybrid perovskites and the resulting and the selected charge extraction layers in conventional device architectures, already has been proven effective in terms of not only maintaining their competitive performances that I would not like to focus on as I would like to target the discussion on the molecular level in the fundamental research, but still illustrating the capacities in terms of not only their competitive performances, but ultimately operational stabilities, which now in terms of their representation, we're absolutely challenged, and I look forward to the discussions further in that regard. So nonetheless, you can see here and you can appreciate the capacity of these systems to achieve some of these effects in functional devices that have been directly related to their ability to interact with some of these A cations and metal cations at the interface with hybrid perovskites. To really demonstrate this and have the confidence in terms of this advanced molecular design and to guide it in the future, this research relies heavily on understanding these atomic level interactions. And for this purpose, we rely on solid state NMR spectroscopy, which I would like to briefly here illustrate in terms of its capacity, which involves monitoring different NMR active nuclei, such as, for example, carbon-13, which has been proven very helpful in understanding the binding of A cations, for example, which can be done by monitoring the NMR spectra, carbon NMR in this case, of different precursors, resulting perovskite systems, as well as their mixtures with the host moiety, in this case the crown ether, illustrated here by this code DB24C8, which now enables us to identify different environments that would correspond to the system binding a specific A-cation. Now, in order to really build confidence, apart from identifying these new environments and comparing these different NMR spectra, we can also perform two-dimensional NMR spectroscopy analysis, which essentially refers to monitoring the exchanges through space between two nuclei that results in the exchanges in magnetization that manifest in these two-dimensional NMR spectra, in this case proton-to-proton spin diffusion experiments. They manifest in the formation of these off-diagonal signals that essentially correlate now these chemical environments of the species, in this case A-cation, and the host moiety, suggesting their presence in the nanoscale proximity within the same phase, which offer us the confidence of the presence of this interaction. And this can be done with a number of different nuclei to identify these species with confidence, including lead NMR, for example, for lead cation binding, including both the one-dimensional NMR spectra and the two-dimensional, in this case now, heteronuclear proton-lead heteronuclear coupling, where we correlate the proton environments of the host to different lead species, identifying their presence within the same phase, enabling us to assign these interactions to this particular binding of the species. Now, the capacity of this system, importantly, to now competitively bind both A-cations and lead cations, offer the possibility now for it to serve as a molecular vehicle or a shuttle to deliver specific ions within the hybrid perovskite framework, and this particular cesium cations, which in fact were used for this formamidinium lead iodide perovskite composition most of you must be familiar with, which is one of the most attractive ones when it comes to the ideal optoelectronic characteristics for the purpose of photovoltaics, but which is notoriously stable, as its perovskite form cannot even thermodynamically be accessed at ambient conditions, which can be to an extent circumvented by using smaller cesium cations, yet at the expense of its optoelectronic characteristics, which is something that we circumvent by relying on now this gradient of cesium cations to really stabilize the resulting material without compromising the beneficial optoelectronic characteristics, further enabling competitive performances and maintaining these large beneficial operational stabilities even at elevated temperatures. Highlighting the importance of now these multimodal host-gas complexation strategies relying on a synergy between these hosts binding these defects at the interface, the gas stabilizing the bulk perovskite, and the host-gas complex triggering this in the first place. One of the motivations for me to bring this example to your attention is that these strategies are in this case not only relevant for the photovoltaic performances or stabilities, but also potentially increasing the sustainability of these technologies, as when we would immerse these solar cells in water, we could see that the release of lead ions is substantially reduced, suggesting perhaps that we could rely on some of these strategies to suppress their negative environmental impact. Now, this illustrates the capacity of supramolecular engineering in the context of not only crystal engineering and controlling the morphology, but also the defect chemistry, as well as the stability of these systems through these intricate understandings of the atomic level interactions, which now open the path for taking a step beyond the use of these small substoichiometric amounts of molecular modulators at the surface of hybrid perovskites to fully incorporating them within the extended perovskite now architectures in order to build extended hybrid materials, where now the organic component plays a role within the hybrid perovskite structure by templating the perovskite architecture and further contributing to its stabilization in different types of perovskite architectures, either these bifunctional so-called RP or a monolayer bifunctional system, better known as Dine-Jacobson or DJ architectures, in both of which cases now stabilizing the system through increasing the hydrophobicity of the organic phase, as well as its ion impermeability, which also opens the possibility to tailor further the optoelectronic characteristics of these systems more directly by controlling the assemblies of the organic components, which is something that I would also briefly like to illustrate in an example which so far challenges the two typical examples that have been used in the literature so far for maybe those that are more interested in the chemistry in the room, being these butyl ammonium or phenylethyl ammonium-based systems as these spacer moieties, we have tried to extend and further analyze in terms of extending the range of possibilities and the functionalities on these particular components, involving a number of different now organic spacer moieties, some of which are illustrated here. So for instance, strengthening these van der Waals interactions by introducing these carbocyclic elements, or tailoring further these aromatic interactions in order to achieve not only the Rudess and Popo, but different Diane-Jacobson-based phases. Especially by relying on these pi-based interactions that I highlight as we've been hoping to also relate to them when it comes to controlling the ionic properties of these systems, and which essentially refer to now changing the polarity of the typical aromatic ring in order to strengthen these, inverting the polarity in order to strengthen these interactions and make accessible more of these parallel interactions that rigidify this organic layer and further stabilize the resulting systems. And for this purpose, we relied on two different model systems that are illustrated here. So these typical phenylethyl ammonium and the perfluoroarene-based systems, both of which form well-defined perovskite phases, and which were, in the case of these layered two-dimensional perovskites or mold stable phases, typically used in functional devices as, again, interlayers on these three-dimensional perovskite architectures, enabling them to further maintain these stabilization factors while also reaching competitive photovoltaic performances. This is primarily ascribed to the capacity of these systems to maintain the beneficial optoelectronic characteristics of these systems, as well as their three-dimensional structure, despite the capacity of all of these spacers to really form well-defined two-dimensional perovskites. However, in this case as well, it is important to realize that when we use typically X-ray diffraction for the analysis of these systems, we still analyze primarily the inorganic phase. So in order to truly understand the importance of the organic components within these systems, it is much more important to complement this analysis that is conventionally done with the perspectives from the NMR spectroscopy that I want to highlight on this occasion. And for this purpose, the presence of some of the elements like fluorines offers not only a gauge to control the assemblies, but also a label to follow some of these interactions. And in this case, by monitoring once more these exchanges in polarization between the fluorine and the carbon that can take place only within their nanoscale proximity, such as by when forming these pi-based interactions. And as a result, we can observe the presence of additional signals in the corresponding NMR spectra that can be associated with some of these exchanges in both the mixtures of the neat organic components as well as the hybrid perovskites. However, here, this example opens another question on, do we really understand these structures? As when we look at the other spectral characteristics, we can see that they're fairly comparable, which makes us ask ourselves, is this nanoscale proximity really the result of forming the desired supramolecular assembly? Requiring us to take a step further in the level of this molecular understanding by complementing this with another technique known as NMR crystallography that I would like to bring to your attention, which now involves NMR spectroscopy and complements it with the theoretical insights and prediction of a number of these model structures and the calculations of the corresponding NMR spectra by looking into a number of different configurations, learning from their crystal structure, some of which are illustrated here. Now these fully alternating arene, perfluoroarene-based systems, checkerboard structures, and others, by looking into different configurations within this crystal structure that leads to now these beautiful linear correlations between the calculated and experimental values for both carbon and fluorine spectra, and to ultimately give us the answer of what is the most likely structure that we observe in these films or mechanosynthetically prepared powders, which is based on these analyses suggested to be the structure that is also the most thermodynamically stable or desired for our case, being this fully alternating arene perfluoroarene structure. But when we look carefully into what NMR crystallography offers us, we see that the best match in this case, in fact, comes from the mixtures of neat arene and perfluoroarene moieties, suggesting that these systems are in fact, well, nanosegregated. They feature narcissistic self-sorting that favors alike systems inside the solid state. And this is not only the case for Drilled and Popper systems, but it's also general for more Jacobson architectures, which really challenges our perspectives and brings a level of complexity when it comes to these systems, targeting their design, but implying the necessity to further look into these atomic level interactions to understand and identify the factors contributing to their effects in the materials and the resulting devices. Which also highlights the main features of these supramolecular strategies in general, which is that these weak non-covalent interactions, despite their weakness, are multiple in these materials, and as a result can and will make a difference. So it's worth looking more closely into understanding them to be able to control these materials. Now with that in mind, this also provides the possibility to not only control these assemblies, but to rely on the powerful features of this toolbox to not only now address the pressing challenges, but also take a step further in enhancing the functionalities of these systems, which involves, for instance, introducing additional functions within these organic moieties in the form of a variety of different functionalities of the organic components that enables tailoring these optoelectronic properties that are primarily defined by the, as I mentioned, metal halide orbital overlaps, and which can be changed in terms of even their basic band gap and other characteristics by enabling the organic component to really contribute to some of these features, as illustrated with some of our recent work, where we can rely on a different electroactive organic moieties, including, for example, here, given an example of a typical electron acceptor, or NDI, to tailor these properties, showing the possibility to really form some of these now changed electronic structures of these systems and open the possibility for these, especially with the electroaccepting or donating moieties of these components, to not only serve the stabilizing or structure templating role, but perhaps even selective charge transport in the resulting devices that I hope to discuss further. So this involves a number of different functionalities, from electroactive, photoactive, chiral, or other moieties that can respond to different external stimuli, from charge, voltage bias, light, or mechanical stress or external pressure, as illustrated in some of our recent reports, suggesting that these dynamic structures could even reversibly change their properties, including the optoelectronic characteristics, as recently illustrated by this example coming from this beautiful collaboration, showing the possibility to really tailor their optoelectronic characteristics reversibly, even in these relatively low pressure increased ranges, which correspond to the level of strain associated with some of these structural rearrangements in these molecular systems, offering now an entirely new platform for hybrid perovskites as framework materials to incorporate different stimuli responsive systems that can open the perspectives even well beyond photovoltaics. Now, with this series of examples, I hope to have provided you with a brief overview of some of the capacities of this molecular and supramolecular level engineering in controlling these hybrid materials, and through their understanding, offering the possibility to further control their photovoltaics properties, stabilities, as well as further advancement towards smarter nanotechnologies. With that, I wish to thank all the colleagues and collaborators once more contributing to this work, and also further, while strengthening my belief in the importance of international and interdisciplinary collaboration when it comes to tackling these complex contemporary challenges. With that, I wish to thank you all for your kind attention while I look forward to our discussion. Thank you.
Thank you. Yes. Thanks, Jovana, for a fantastic talk. And I really like the combination of state-of-the-art solar cells, but also really fundamental chemical understanding of the systems that we work in. I'm sure there are questions. Who would like to start? Erik.
Yeah, I'm wondering in these mixed systems, do you selectively kind of convert the 2D material at the interface, or does it go through the whole phase? And when you check this with NMR, I guess you're seeing bulk, not interfacial effects. So, yeah, how do you think about that, both from the fabrication standpoint and also the characterization?
Thank you for this question. I think this is very important. I believe I should be having the description here. So normally when these samples are prepared, as most of you are familiar with, it's a thin film preparation with simple spin coating and using complementary solvent to apply the phase. But at the same time, we complement all our measurements with mechanosynthetic preparations, which involves practically grinding the materials in absence of any solvent in order to get higher quantities of materials, which are also then compared by complementary methods. So we also prepare films, for example, that are scratched off and use this powder. So this is necessary for NMR experiments. So this is where I agree. We do not really immediately assess the interfacial effects unless using the films and the NMR instruments, but we deduce this through complementarity of the methods. Now, especially with these mixed systems in terms of the 2D materials, we apply two different approaches to this. One of them is indeed using the organic spacer and forming by this deposition method an overlayer intrinsically by applying it on the three-dimensional system. So this is one of the approaches. The other approach is actually preparing mechanosynthetically a two-dimensional system and simply applying the film of a two-dimensional system to really then gauge whether there is the effects, which is also important for also solubility control when it comes to preparing the powders. So in terms of the preparation, these are the approaches to then deduce.
Okay, I saw a question by Esther.
Oh, thank you, Paul. Sorry. The first was off. Well, great talk, very inspiring. I think it's a great mixture between fundamental and applied insights. When using the NMR, you showed essentially the time average results, right? So could you also use it to see a bit of the dynamics in the system, because that's the most important part of the perovskites?
That's an excellent question. At the moment, this is mostly the indeed time average, and the effects that we were looking into are also a sufficiently long time scale that we do not really need to monitor in situ. There are ongoing efforts to really be able to do this. There are very few groups that could afford to do this in terms of monitoring them, especially in the films or devices, upon exposure, for example, to different stimuli. So there are some ongoing attempts to be able to do this more with the time result.
Because especially for the structural characterization, what you then figure out is just a time average structure which might not even exist, right? If the system just oscillates between this and that, and then you see the middle, that's kind of common for perovskites as well.
Yeah, it's a very good point. I think for the examples that I illustrate, this is not a concern. But indeed, when going into more addressing some of these dynamic functionalities that I hinted upon, where the system changes in the structure, for instance, during exposure to different external stimuli, this is the point where this is absolutely important to monitor. So, thank you.
Okay, we're almost out of time, but I'll take the chance as the chair to ask the last question. Because you, in your last slide, you said beyond photovoltaics. Can you mention maybe your craziest idea for what these systems could deliver for perovskite devices?
I guess we should have enough time to discuss this in more detail, but definitely when we speak about smart systems and devices, it's about complementing this energy harvesting component of photovoltaics with other functionalities, including memory, as you're familiar with, sensing as well, and powering some of our infrastructure, especially by benefiting on these of the flexibility of these systems as well. So happy to discuss this further.
All right, many things to research. Thanks very much, Jovana, for a great talk.
Thank you.